Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 23 on the NPTEL course on fluid mechanics for chemical engineering undergraduate students. The topic of our discussion in the last lecture was differential momentum balance, and we were proceeding towards the derivation of the complete differential momentum balance, and in that context we introduced the notion of the stress tensor. Okay. The differential momentum balance is essentially derived, the way we did it is to take an infinitesimal control volume of a simple geometry, let us say cube, okay, and of sides delta x, delta y, delta z in the 3 coordinate directions, that is the volume of the cube, delta x times delta y times delta z. And essentially we wrote down the integral momentum balance as applied to a control volume in the limit as the size of the control volume shrinks to a point. Okay. Then we obtain the following simplified relation. We obtain the fact that sum of all forces acting on this control volume is equal to rho times the substantial derivative of velocity times del v, where del v is the volume of the control infinitesimal control volume. Now, there are two contributions to forces acting on the control volume. One are called body forces, the other types of forces are called surface forces. Body forces, a common example is gravity. Okay. So, if you have a fluid with density rho present in the control volume and the acceleration due to gravity vector is g, then the force acting on this control volume is mass times g, mg, mass is rho times the volume. So, g is acceleration due to gravity. This is the body force if the body force is gravity, is due to gravity. There could be other body forces such as electrical body forces present in ionic liquids or magnetic body forces. Those will not be of concern to us in this introductory course. Okay. But the most common body force that is encountered in many applications is of course gravity. So, that will be the force that we will include in this discussion in our course. Okay. Now, surface forces are a little more tricky. Now, the surface forces are due to the fact that suppose you have a surface, okay, of that cube which we just drew, and let us draw it the full cube. Okay. There are 6 faces to the cube, okay, x, y and z. Okay. So, each face is denoted by a unit outward normal. Okay. So, this face has a unit outward normal n is in the plus I direction, whereas this face has a unit outward normal n is in the minus I direction. Likewise, this face has unit outward normal n is in the plus j direction, and this face has unit outward normal in the minus j direction. Okay. Likewise, you can do it in the plus k and minus k direction. I will refrain from doing that because it will reduce the clarity of the picture, because one cannot draw 3-dimensional pictures very well in a paper. Okay. So, I will just leave it like this. Now, on each face in general, the force exerted by the fluid that is present outside on this face can in general be in some direction. Okay. That force is, since we are considering only infinitesimal forces, I will denote it with a delta f. Okay. The force can act in general on a given surface in an arbitrary direction. This force, okay, acting on a surface whose unit normal is in the direction n can have 2 components in general. Suppose I take an arbitrary surface, okay, of area delta A and unit normal n. Okay. there can be two contributions to the forces. One is the direction along the normal, those are called the normal forces, and then there are two tangential directions to this surface. So, there will be two components along the direction of the tangent. So, in general you will have delta f t 1, delta f t 2 along the two tangential directions on the surface. Okay. So, the normal forces are predominantly due to pressure, because pressure acts purely normally, plus also due to the fact that there could be normal viscous stresses. The tangential forces are purely due to, or also called as shearing forces or shear stresses, if you define it in terms of per unit area. These are only due to viscous stresses in a fluid. Okay. So, it is normally convenient to write the force per unit area as the normal force per unit area sigma n as limit delta A tending to 0, okay, delta f n by delta A, and likewise the shear stress is denoted as tau n 1 is limit delta A tending to 0, delta f t 1. Okay. So, tau t 1. Okay. Let me explain the notation. This denotes the fact that you are considering a surface whose unit normal is in the n direction, and this is the tangential vector in the one direction, and that similarly there is also a tangential force in the other direction. All we are saying is that for any given plane, any surface with an arbitrary orientation n, the force that acts on that surface due to the fact that fluid is the neighboring fluid, the force exerted by the neighboring fluid on this surface could have three components, one along the normal and two in the two tangential directions along the surface. That is all we are saying. But now we have considered a cube with 6 faces in our control volume, x, y and z. Okay. So, each face will have 3 components. Okay. This face will have the unit normal is in the plus I direction, okay, and in general the force exerted will be, okay, the force exerted will have 3 components. So, the 3 components of the force are, we can write this as one along the normal direction, which is actually the x direction here, because that is the direction of the unit normal, and then the 2 tangential directions are y and z. So, delta f y and delta f z. Okay. So, we can write 3 components of the stresses, the force per unit area, as follows: sigma x x. Okay. So, let me write the 2 x's in 2 colors, sigma x, and I will explain you the reason. Let me write it slightly bigger. Sigma x x is equal to limit delta A tending to 0, okay, delta A tending to 0, where A x is the, let us say this is the area of this face with unit outward normal in the plus x direction, delta f x by delta A x. This is the normal component to the stress acting on that surface. The shear stresses are usually denoted by tau, the Greek symbol tau. Okay. So, now I am going to use 2 colors to the 2 subscripts, tau x y, okay, is equal to limit delta A x tending to 0, because that is the face we are considering, but the force is now in the y direction. The area on which the force is acting is in the x direction. Similarly, you can have tau x z is equal to a limit delta A x tending to 0 delta f z by delta A x. Now, let me explain the colors for the two subscripts. Let me explain the reason for the two subscripts. The subscripts in the orange color refers to the direction of the unit normal to the surface, the unit outward normal to the surface on which we are considering the forces. Okay. So, this tells you the orientation of the surface. Surface orientation. Okay. Okay. Now, that is the purpose of the first subscript. The second subscript, the green subscripts, tell you the direction of the forces. The forces can act in either x, y or z direction on a surface whose unit normal is in the plus x direction, which is I. So, this on this surface you could have forces with 3 components. So, therefore, you need 2 subscripts to denote the 2 issues, that is, one is the direction of the force, the other is the direction of the unit outward normal to the surface on which we are considering the force. Likewise, you could also write tau y x sigma y y tau y z. This is you consider a face whose unit normal is in the j direction, and you are considering the forces in the x, y and z. So, the first subscript, okay, denotes the direction of the unit outward normal, and the second subscript tells you the direction of the force. So, you need 2 subscripts, and likewise you can have in the on a plane whose unit normal is in the z direction, that is plus k, okay, tau z x tau z y and sigma z z. Okay. So, as the control volume shrinks to a small point, okay, the forces on this tiny cubic volume element can be summarized as an array of numbers sigma x x, tau x y, tau x z, sigma tau y x, sigma y y, tau y z, tau z x, tau z y, sigma z z. Okay. So, this is an array of numbers that describe the state of stress on a cubic volume element with nicely defined surfaces along the 3 coordinate directions x, y and z namely. Okay. Now, what is this collection of the state of stress present in a fluid is called the stress tensor. Okay. Why is it called a tensor? It is because of the following reason. If you have a vector like velocity, you can write it as v x times I plus v y times j plus v z times k. Okay. You need only one subscript to denote the direction of the components in which the velocity is pointing. Velocity is a vector, has only one direction associated with it, one physical direction associated with it, namely the direction of the velocity itself. But if you consider something like a stress, okay, which is denoted with two underlines to denote that it is something more higher than a vector, it is actually a tensor because it has 2 physical directions associated with it. associated with it. So, velocity is a vector, stress is a tensor. Okay. Now, what are those two physical directions? The two physical directions are the direction of the unit normal on which the force is acting and the direction of the force itself. Okay. Stress is force divided by unit area. Force as a vector has a direction and the area itself has a direction because of its orientation. Now, so at each and every point in the fluid, if one has the knowledge of this matrix or the tensor sigma x x, tau x y, tau x z, tau y x, sigma y y, tau y z, tau z x, tau z y. Okay. If one has the collection of this, one has an information about these 9 elements, then there is a result due to Cauchy which states that if I have at a given point a surface with arbitrary orientation, that is, you have put a coordinate system x, y, z, but this orientation of the surface is not along any of the 3 directions x, y and z, but it is an arbitrary orientation n x times I plus n y times j plus n z times k. It is oriented in an arbitrary fashion, not necessarily along one of the 3 coordinate directions. Then, and the area of the surface is delta A, let us say. Then what is the force? Okay, the force on this surface will in general have 3 components in the x, y and z direction. The question one can ask is, what is the force acting on such a surface? What is the force per unit area? What is the stress acting on such a surface? The answer due to Cauchy, which I will not derive, is that simply take the local value of the stress on this surface, take the stress tensor acting at that point. So, remember this is an infinitesimal, it is a point and you have an infinitesimal area surrounding that point. Okay. So, at that point you should know what is the stress tensor sigma x x, tau x y, tau x z, tau y x, sigma y y, tau y z, tau z x, tau z y, sigma z z, and according to Cauchy's result, you simply have to do a matrix multiplication of the 3 components of the unit vectors, okay, with the stress tensor. Okay. This is like a matrix multiplication of a matrix 3 by 3 matrix with a 3 by 1 vector. So, the answer will be a 3 by 1 vector, okay, which is this. So, by having the knowledge of the stress tensor at a given point, which the stress tensor at a given point in the Cartesian coordinate system tells you what are the forces per unit area acting on directions which are perpendicular to the 3 unit vectors in the Cartesian frame of reference. But if you have an arbitrary phase, arbitrary area, then you can get the force per unit area acting on that surface with an arbitrary orientation in this fashion, but by merely multiplying the elements of the stress tensor or the stress matrix with the column vector containing the components of the unit vector. Okay. So, that is the power of doing the Cauchy construction. Now, having understood what are the stresses acting on the surface, also the sign convention for the stress, okay, which we mentioned last lecture. Suppose you have a surface that is pointing in the plus j direction, and suppose we say that tau y x is 10 Newton per meter squared. This is the x direction, this is the y direction. What this means is that you have a force. So, y represents in our convention the direction of the unit normal. So, that is in the plus j direction, x tells you the direction of the force. So, if it is positive, tau y x is positive, then the force of 10 Newton per meter squared, force per unit area, that is, it acts on the plus x direction on a surface whose unit normal is in the plus y direction. So, if you have both the direction of the unit normal, and so if you have the answer of the stress tensor to be positive, that means that both the direction of the unit normal and the direction of the force are positive. Or it could also be the following, that on the same surface at the same point you could consider a unit vector in the minus j direction. You could consider, and each plane has two unit normals, one is the normal pointing in outward direction, other is the normal pointing in the inward direction. So, if you consider the unit vector to be pointing in the minus j direction, then the force acting on this surface is in the minus x direction. This is plus x. The magnitude of the force is 10 meters, 10 newtons per meter squared. So, if somebody says that you have a force or stress tau y x is plus 10 Newton per meter squared, okay, it could either mean that in this, it could either mean that a force of plus 10 is per Newton per meter squared is acting in the plus x direction in a surface, on a surface whose unit normal is in the plus y direction, or a force of 10 Newton per meter squared is acting in the minus x direction on a surface whose unit normal is in the minus y direction. Okay. So, that is the meaning of positive terms, positive stress values. Okay. Suppose you have negative stress values. If somebody says the element of a stress tensor is negative, that means the following. If you have a unit normal in the plus j direction, the force is acting in the minus x direction, and the magnitude of the force is plus 10, magnitude of the force is 10, okay, or vice versa. If you consider the unit normal in the minus j direction, then the magnitude of the force is in the plus x direction. The force acts in the direction of the force is in the plus x direction, while the magnitude remains 10. Okay. So, if the stress value is negative, then it means that the direction of the force and the direction of the unit normal are opposite to each other. If the stress value is positive, then the direction of force and the direction of unit normal are along the same direction. They both could be positive here, or both could be negative. Here, if one is negative, the other is positive, and vice versa, if one is positive, the other is negative. Okay. So, that is the sign convention for the stress tensor. Okay. Having done all this, we went back to the differential momentum balance, which simply said that is rho g times delta v plus the surface forces acting on the cube. Okay. Now, the way we did was to consider each face of the cube, take each direction x, y, z. So, we first wrote down the x momentum balance. How do we do that? We did that by saying that take the x component of this equation, delta v is rho g x delta v plus all the surface forces acting along the x direction on this control volume. What are the various surface forces acting on the x direction? On this face there is a force sigma x x, on this face there is a force tau y x, on the front face there is a force tau z x. All these are pointing, the direction of the force is, remember, the second subscript. So, all these are pointing in the x direction. Okay. But there are not just three faces, there are also these opposite three faces, which for which the unit normal is in the opposite direction. We have to consider those forces as well, and then use the Taylor series expansion for tau at x plus delta x in terms of tau at x to arrive at this simplified relation. We finally ended up with this equation, rho du dt delta v is delta v times rho g x plus partial sigma x x by partial x plus partial tau y x by partial y plus partial tau z x by partial z. Okay. So, the volume of the control volume drops out of the equation, because both terms are multiplied by the same quantity. Now, we also said that in a static fluid, the only force that is acting are the normal pressures. So, the stress tensor becomes, and this pressure acts inward. So, you will have a minus P. Okay. In a static fluid, the stress tensor is just this. In a flowing fluid, under flow, we want to write the stress tensor as this, which would be the case if the fluid were to be static, plus stresses that come up because of the viscous resistance of the flow of the fluid. So, this is written as this is x y. So, sigma x x becomes minus p plus tau x x, sigma y y becomes minus p plus tau y y, and sigma z z becomes minus p plus tau z z. Okay. Under flow, therefore, these are the terms that will happen only, these are non-zero only under flow, non-zero only if flow exists. Okay. These are the viscous stresses, the stresses that come about because a fluid resists motion, continuous deformation. So, these are the viscous stresses that are generated by the fluid to resist the deformation. Okay. So, then we wrote rho du dt is minus partial p partial x plus rho g x plus partial tau x x by partial x plus partial tau y x by partial y plus partial tau z x by partial z. Okay. This is the first term, the x component, the y component of the momentum balance this is x y, and the z component Okay. So, these are the three momentum equations, the differential form, the momentum equations. These are also sometimes referred to as the Cauchy momentum equations. These are the differential form of the momentum balance. Okay. These are also called the Cauchy momentum equations. And we also have the mass balance, if you remember, for an incompressible fluid. Okay. The continuity equation, which in Cartesian coordinate means so we have 4 equations, 3 components of the momentum equation and 1 continuity equation. So, you have number of equations is equal to 4 so far. And the number of unknown variables that we have, we can count as follows. Okay. 3 velocities, the 3 components of the velocities, 1 pressure and the 9 components of the stress. Okay. So, the problem is highly underspecified because the number of equations so far is less than the number of unknowns. So, we cannot solve this problem. Okay. So, we cannot solve this problem as such right now. Okay. So, that is the idea that we cannot solve the problem because you have far too equations than unknowns. Now, we have to look at the problem why we have this situation, okay, that we are not able to solve the problem completely, and that is because we have not said anything about whether the material is a fluid or a solid even now, because all that we have done is to apply Newton's second law to a control volume and then took the limit as the control volume shrunk to 0, size 0, but nothing has been told so far whether the material that resists deformation is a fluid or a solid. That is, the constitutive nature of the material has not yet figured in our framework. So, we need to specify something about the nature of the fluid, okay, that will relate, okay, the stresses to the velocities, okay, and thereby we will be able to achieve some closure. But before that, we can also write down equation for angular momentum that will tell us that tau y x is tau x y, tau z x is tau x z, tau y z is tau z y. That is, the stress tensor is a symmetric tensor, that is, the matrix of elements is a symmetric matrix. That is, you have, whether you write it like this, tau x x, tau x y, tau y x, whenever you write it like this, these two terms are the same, okay, and these two terms are the same, the green terms, and likewise these two pink terms are the same. Okay. They are the same because it turns out that when you do the angular momentum balance, and if there are no internal couples that generate angular momentum within the fluid, which is true for almost all fluids, okay, then one can show that the stress tensor is identically symmetric always. So, we are left with only a symmetric matrix has only 6 elements, because there are 3 equalities that relate that give you 3 additional equations. Therefore, a symmetric matrix has only 6 independent components as opposed to the 9 independent components for a second order tensor, 6 independent components. But nonetheless, we are still left with more unknowns than the number of equations that we have to solve them. So, we have to specify what is called the constitutive relation. Okay. In this context, one way to approach the problem of constitutive relations is to do experiments on known fluids and try to correlate the stresses with velocities and so on. That is one way, and that is often done in labs to characterize fluids. The other way is to guess the form of constitutive relation based on some general principles. Okay. Now, let us try to guess the form of constitutive relation from an intuitive or physical point of view. Now, firstly, let us take a very simple system, that is, flow is happening between 2 plates, okay, x and y. Bottom plate is stationary, static, top plate moves with a velocity v. Okay. So, you will have a velocity that looks like this, okay, in between the 2 plates. Now, the question that one can ask is, the relevant component of the stress is you have a plate whose unit normal, I mean I am just drawing a cross section, actually it is a plate, it extends, whose unit normal is in the plus j direction, and the direction of the stress would be in the plus x direction. So, the component of stress that will be of interest is tau y x. Okay. Now, what should tau y x be a function of? Okay. What can tau y x depend on? We can say that tau y x will depend on the velocity, okay, velocity of the flow, but that is not all, because that does not tell you the whole story. Okay. Because if it just depends only on the velocity, then you can say that, well, what about the distance between the two plates? Okay. Will it be the same if I have the same velocity, but a very large distance? Will it be the same if I have a very small distance? So, clearly the velocity tau y x cannot be a function only of the velocity. Okay. Somehow the distance between the two plates have to come in. Okay. Also, from a physical point of view, the stress cannot be in a fluid. If the entire fluid moves with a constant velocity, then there cannot be any internal viscous stresses generated, because that is merely rigid body motion. Okay. Stresses are generated in a fluid only if there is relative deformation between 2 points. Okay. 2 points move past each other relative to each other. Okay. Now, that, so only then stresses will be, viscous stresses will be generated. Now, that part is accurately captured by what is called the gradient of velocity. So, stresses in a fluid cannot be generated purely by rigid body motion of the entire fluid. There has to be relative deformation between 2 points in a fluid, and that is captured by what is called the gradient of velocity. That is, if you have flow in the x direction, the velocity component of interest is V x, the x component of the velocity. If the x component of the velocity is different at two different points, then we say that there is a gradient. So, this is denoted by dV x by dy. Okay. So, in this particular case, there is indeed a variation in velocity in the y direction. So, there will be stresses that are generated because there is a difference in velocity between two different points in the fluid. If you say both the plates are moving with a constant velocity v, then of course, there will not be velocity gradients and there will not be any viscous stresses, because this amounts to merely moving the entire fluid as a rigid body. Okay. So, only gradients of velocity can generate stresses, not absolute velocities. So, in this simple context which we just discussed, okay, let me just show the picture here itself. Okay. You have two plates, one at y equal to 0, other at y equals h, okay, and the top plate is moving with a velocity v. Then the relevant component of the stress is tau y x, because you are considering the force acting on this part of the fluid, that is the top surface, okay, on in the x direction, because that is a relevant component of the stress. So, tau y x must be proportional to dy. Okay. The constant of proportionality is called viscosity of the fluid. This is called the viscosity. Okay. Now, the dimensions of viscosity can be estimated as follows. Stress is force per unit area. This is force divided by area. The dimensions of velocity gradients are simply 1 over time. Okay. So, the dimension of viscosity, stress can be written as m, okay, is times t to the minus 1. If we take to the other side, then the dimensions of viscosity is ml to the minus 1, t to the minus 1, kg per, the units in SI units are kg per meter per second. Okay. So, this is a material property of the fluid, it is a material property of the fluid. of the fluid. Okay. So, this is the simplest expression because we considered a relatively simple flow between two parallel plates, the flow is only in one direction, and but in general the flow can be much more complex. But before I go to the complex situation, this is often called the Newton's law of viscosity. Okay. This is merely an expectation from our side, intuitive expectation from our side. It is not guaranteed that all fluids should obey this expression, this relation. In fact, many fluids do not. Okay. For example, if you consider fluids like toothpaste or shampoo or ketchup, they do not obey this relation, they are much more complex. Okay. But many simple fluids like air, water, glycerine and so on, they do obey this simple relation. Such fluids are called Newtonian fluids. The fluids which obey the Newton's law of viscosity, which says that the stress, the shear stress is directly proportional to the velocity gradient, and the constant of proportionality, which is a true constant, is independent of the flow parameters like velocity or velocity gradient, okay, is called the viscosity of the fluid. Okay. Now, this is for the simplest case, but Newton's law must also be written for the most general case. So, the Newton's law of viscosity for the most general case where the stress, the flow can be in all the three directions. Okay. Tau x y tau. Remember, the stress tensor is symmetric, okay, from angular momentum balance. So, let us hope that I have used mu. Yeah, mu is the symbol used for viscosity normally. Okay. Tau x z is tau z x is mu. Tau x, sorry, tau y z is mu. Okay. And then you have the normal stresses, tau x, normal viscous stresses is 2 mu. Okay. Is 2 mu, tau z z is 2 mu partial w by partial z. Okay. And this is the constitutive relation. These are called constitutive relations because they tell, they have some information about the constituent material that that make up the fluid. These are called constitutive relations, and the ones we have written are for a simple Newtonian fluid such as air and water. Okay. Now, we have written all the stresses in terms of the velocities or gradients of velocity. So, now we have exactly the same number of equations as you have unknowns, because you have 3 momentum equations and 1 continuity equation, and we have 3 components of velocity and 1 pressure as the unknown. Okay. So, that completely specifies the problem. Okay. So, now let us substitute all this in the momentum equation. So, let us go step by step. For the x momentum equation, plus rho x plus we had partial tau x x by partial x plus partial tau y x by partial y plus partial tau z x by partial z. Now, let us substitute all the 3 components. So, let us, I am going to focus only on this term now, okay, and then we can substitute this back in this expression. I am going to substitute each terms. Partial tau x x is 2 mu partial u by partial x plus partial tau y x is mu plus partial tau zx is mu plus partial u partial z. Okay. Now, I can write the first term as, since it is 2, I can write it as sum of two terms, partial x of mu partial u partial x plus again the same thing now. In all these equations, I am going to take out, I am going to write the first term separately, all the other two, terms. I am going to write separate out the first term plus partial y of mu partial v partial x plus partial z of mu partial w partial x, but still we have those two terms, plus partial y of mu partial u partial y plus partial z of mu partial u partial z. Now, the order of these derivatives, partial derivatives are interchangeable. So, let me write this as partial x, and we will assume that mu is constant independent of spatial positions. So, we can pull out mu, okay, of partial u partial x, that is from this term. Okay. We also have, if you interchange these two partial derivatives, then you will have partial x of partial v partial y, and likewise from this term, if I interchange the partial derivatives, partial x of partial w partial z plus mu, then you can write this equation, this term as partial squared u partial x squared, this term as partial squared u partial y squared plus this term as partial squared u partial z squared. Now, this term is identically 0 from continuity equation. Okay. The mass conservation equation says this is identically partial u partial x plus partial v partial y plus partial w partial z is nothing but del dot v is 0. Okay. So, if you look at this expression, okay, the only thing that survives is that this becomes mu partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared. So, I am going to write the x component, okay, of the momentum equation after using the constitutive relation for the Newtonian fluid as rho, the substantial derivative of the x component of the velocity is partial p partial x, the pressure gradient term, rho g x, the gravity term, plus mu partial squared u by partial x squared plus partial squared u by partial y squared plus partial squared u by partial z squared. Okay. This is nothing but the Laplacian del squared of u, where del squared is the operator partial squared by partial x squared plus partial squared by partial y squared plus partial squared by partial z squared. Okay. So, the x component of the momentum equation can be simply written as rho substantial derivative of the velocity is minus partial p partial x pressure gradient term plus the gravity term plus the viscous stress term, which becomes like this. So, I can write similar equations for the y component of the momentum equation just by analogy. one can of course go through the algebra in the same manner and you will end up the same thing. Okay. This is x component, y component, okay. This is the z component, mu del square w, and of course one has the continuity equation, mass conservation equation, the mass balance, differential form of mass balance, which is partial u partial x plus partial v partial y plus partial w partial z is 0. Okay. Now, I can write this in a coordinate free form, just as the mass conservation equation in a coordinate free form became del dot v 0. I can multiply these three components by their unit vectors and add them up, and I will get the following equation: dv dt is minus gradient of pressure plus rho g vector now plus mu del squared velocity vector. Okay. These two equations are called the Navier-Stokes equation for an incompressible fluid. For an incompressible Newtonian fluid. Okay. So, this is the mass balance, this is the differential momentum balance. Okay. So, the next task for us is to understand these equations by providing some solutions of these equations in simple physical context. We will continue this in the next lecture.